Good day to you. My name is Dick Stacey, and today I'm going to give you an introductory lecture on rock mass classification in rock engineering. This is the way that I would do it, and I also want to give you an indication of how you can use rock mass classification in rock engineering. This shows you a massive outcrop of rock. Rock mass classification is not applicable to this type of rock mass. Here you see failure which has resulted in a vertical pit mine as a result of sliding on two major weakness planes. Rock masses whose behavior are dictated by planes like these are also not applicable as far as rock mass classification is concerned. However, when a rock mass is intersected by a sufficiently large number of weakness planes, such that rock mass behavior is not controlled by failure on individual planes, the behavior of the mass will tend towards a continuum type of behavior again. However, the numerous planes in the mass being much weaker usually than the rock material, they will have a major influence on rock mass behavior. In such cases, rock mass classification is commonly used to evaluate the rock mass behavior. Rock mass classification puts a number to the quality of the rock mass, i.e. it quantifies the quality. I'm going to ask some questions now, and I will give the answers to those, but you should think carefully about the questions. First question is, what are the factors that control the stability of a jointed rock mass? The answers are block size and shape, the shear strength of weakness planes, and the confining stress. Next question, what defines the size of rock blocks in a jointed rock mass? Numbers of joints and joint spacings. Next question, what controls the strength of joints in a jointed rock mass? The following: roughness, planarity of the joints, the joint surface alteration, joint filling or gouge, if there is any, and the separation between the joint surfaces. Next question: what are the stress controls on a jointed rock mass? There are several of these. In situ stress, the induced stress, particularly in a mining environment where excavation may have affected the stresses around an opening. The next point, water pressure, and finally, dynamic stresses. Rock mass classification puts a number to the quality of a rock mass. It takes into account the block size, the interblock shear strength, and the confining stress, including the groundwater. Before one goes about rock mass classification, one needs to know what is there in the rock mass. And for that purpose, we need to do rock mass characterization. And ideally, what you want to have is a geotechnical database. You need to know the boundary conditions that are acting on the rock mass, and as a result of all that information, to be able to build a geotechnical model, a conceptual geotechnical model. And this rock mass characterization provides the input data for rock mass classification. Rock mass characterization includes measurement of properties of the rock in the laboratory. And here you can see a typical laboratory setup, a press for loading rock samples. Here you see a rock sample in the testing machine, and you can see that there are strain gauges attached to it to determine the deformation properties of the rock. This shows a Brazilian test apparatus for determining the tensile strength of the rock. This is a point load tester which can be used rapidly to determine the point load strength, which can be converted to the uniaxial compressive strength, and these tests can be done out in the field on rock core. They are commonly done by geologists when they're actually logging the core. What are observational indicators of stress magnitude and direction? Because you need that information for the boundary conditions in the rock mass. These are structural geological interpretations which can be done by specialist structural geologists, and breakouts, or we commonly know them as dog ears, in excavations and boreholes, because these give the orientations of the stresses. Here you see a dog ear in a bored tunnel. This was one of the tunnels of the Lesotho Highlands water project, and you can see very clearly that that is on the horizontal mid-plane of the tunnel, which indicates that the stress in that case was a vertical stress. This is an ore pass which has broken out. You can see the dog ears, and you can see there indicated the major stress direction that is causing those breakouts. So this is giving you a visual indication of the directions of in situ stresses. You can see that in typical boreholes, any circular holes, and so on. There is a South African in situ stress database available, and this will allow you to estimate the in situ stress conditions for projects in which no stress measurements have yet been made. This shows a map of Southern Africa, and the red arrows on that map give an indication of the in situ horizontal principal stresses. These are based on measurements that have actually been made at various tunnel, mining and civil engineering sites, as well as interpretations from earthquake seismicity. This shows the relationship between K1 and the depth, K1 being the ratio of the major horizontal principal stress and the vertical stress. And you can see there that at shallow depth there are some cases where the horizontal stress can be very, very much higher than the vertical stress. This is particularly the case in the coal mines, and if you look at some of the others, you'll notice that the platinum mines tend to have stresses where the horizontal stress is approximately equal to 2 to 3 times the vertical stress. This shows a similar result, but in this case K3, K3 being the ratio of the minor horizontal principal stress to the vertical overburden stress. And there you can see the envelopes, both the K1 envelope and the K3 envelope. Other boundary conditions include groundwater, seismicity, and excavations and blasting. Excavations being some things that are going to change the stresses. In rock mass classification, one needs to take into account variability. And we're dealing with natural materials and natural environment. So rock materials have variability. This is the strength, the deformability, their proneness to weathering, and so on. The rock mass structure, that includes fault and joint orientations, their persistence, their strength, their spacing, and so on. And then the boundary conditions. The in situ stresses are going to have variation in them. The induced stresses are going to vary. Water pressures, there will be variation in those as well. And all those variations need to be taken into account. And as in the input parameters to rock mass classification, one needs to take variability into account. In the lecture that follows, I will tend to use average values because it's easier from an explanation point of view. But you need to remember to take into account the variability when you are applying rock mass classification in the future. This shows an outcrop of rock, and I often use it as an example because it is a very clear-cut case. In that slide, you can see that the rock mass consists of cubical blocks of rock, and it's clear that there are 3 joint sets. 2 of these are sub-vertical, and 1 is sub-horizontal. One can get an idea of scale from the fence posts at the top of the slope there, the top of the cutting, and in this lecture we're going to assume that those fence posts are 2 meters high. Obviously you need to take into account the scale of the photograph as well. This just shows another example of a rock mass in which rock mass classification is particularly applicable. It's an exposure in Chile, and it's close to El Teniente mine that uses block caving as a mining method, and rock mass classification is particularly applicable in that environment. This shows a small road cutting, and you can see a very different type of rock mass structure in that case. There are probably 4 or at least 3 plus random joint sets there. Here you see a very closely jointed rock mass, and it has also been blast damaged. I shall use 3 approaches in this lecture. The first is the Q system developed by Barton and his co-authors. The second is the GSI system developed by Everett Hook. And the third is the mining rock mass rating system developed by Dennis Laubscher. And I'll also use Beniowski's rock mass rating system because it is very useful as a means of comparison between the other systems. But I'm not going to go into detail on that method. First of all, I'd like to give you a little bit of background to the developers of these rock mass classification systems and their contact with South Africa. This is perhaps unusual because rock mass classification traditionally has not been used to a great extent in the mining industry in South Africa. That is certainly changing now, but in going through a description of the developers of these, you will see that there was a significant South African input into the development of these rock mass classification systems. This is Professor Beniowski and his wife celebrating his 77th birthday. He was head of the Rock Mechanics Division at the CSIR in Pretoria, and it was while he was there in the early 1970s that he developed his rock mass rating system. This is a poor picture, I'm afraid, but it shows Dennis Laubscher in a draw point in El Teniente mine in Chile. Now, Dennis Laubscher worked up in Zimbabwe on the asbestos mines, and he had been puzzling about how to be able to predict rock mass conditions such that it would facilitate mine operations, the planning of how to get support to the right place at the right time. And when Beniowski's rock mass rating system came on, Dennis Laubscher thought, this is the answer. And he tried to apply it, and he found it didn't work. As a result of that, he then developed his own rock mass classification system using the same parameters as Beniowski, but with different weightings applied to each of those parameters. And the mining rock mass rating system is now developed all over the world. Dennis Laubscher still lives in South Africa. He was a Wits graduate originally in mining geology, and then subsequently did a PhD at Wits University. This is Everett Hook some years ago. Everett Hook is now in his 80s. He lives in Vancouver in Canada, but he went to school in Zimbabwe, in Bulawayo. He went to Cape Town University, where he did his bachelor's and master's degrees, and subsequently a PhD degree. He was head of the Rock Mechanics Division at the CSIR in Pretoria before Beniowski. And Beniowski followed on from him as the head of the division, obviously. And they both did their doctorates in rock fracture. This is Nick Barton, also some years ago, although he looks much the same now, but with grey hair. Nick Barton was a PhD student at Imperial College when Everett Hook went across there from CSIR here to become ultimately the professor of rock engineering at Imperial College in the Royal School of Mines. So that's the link between the developers of these rock mass classification systems and South Africa. So I think South Africa has made quite a contribution to the world in this regard. I'm going to start off with a brief introduction to Beniowski's geomechanics classification system or rock mass rating system, which the main development of that took place between 1973 and 1979. And I know about it well because I actually worked with Beniowski at the time. I was one of his juniors. The rock mass classification is an interesting one. Beniowski approached it by saying, what is important? What are the controls? What are the parameters that are most important as far as rock mass behavior is concerned? And he settled on 5. And he said that there can only be a maximum of 5 because you only have 5 fingers. And if you have more parameters than that, you have to have a notebook with you. And that just makes things more difficult. So he decided on 5 parameters. And the parameters were, as you see, the strength of intact rock material, the drill core quality in terms of the rock quality designation, the spacing of the joints or discontinuities, the condition of the discontinuities, and the groundwater conditions. And then those have various ratings associated with them. So, for example, the strength has a maximum rating of 15 points. Drill core quality, the RQD, a maximum rating of 20. Spacing of discontinuities, 20. Condition of discontinuities, 30. And groundwater, 15. And when you add all those together, you come to 100. So the perfect rock has a score of 100, and a very poor rock is going to be down at a score of 10 to 20, something like that. What will happen then is when this is applied to a particular case, for example, to assess the effect of a tunneling in it, you have to take into account the orientation of the discontinuities. In the classification, it's only the spacing which is taken into account. So the orientation affects the quality, and there's an adjustment applied to that. So you might say there's a 6th parameter which is taken into account. So that was briefly the rock mass rating system developed by Beniowski. The Q system was developed by Barton and his co-workers at about the same time. It was first published in 1974. This is different. It takes into account 6 parameters. It also takes into account the rock quality designation. It takes into account the joint set number, and that is not the number of joint sets, it's a number that corresponds with a certain number of joint sets. It takes into account a number related to the roughness of the joints. That's the joint roughness number. There's also the joint alteration number, the joint water reduction factor, and a stress reduction factor, which takes into account the in situ stress and also the strength of the rock. For those of you who are not aware what the rock quality designation is, it comes from drill core, and if you take a length of core and measure all the pieces of core that have a length greater than 100 millimeters and total those up and divide it by the total length of the core and express it as a percentage. That is the rock quality designation. So an excellent quality rock will have an RQD of 100, whereas a poor quality rock will have an RQD of 20 or something like that. It applies to NX core, which has a 54 millimeter diameter drill size. If you're not able to have core, you can actually estimate the RQD from rock exposures. And this was developed by Palmstrom in Norway. And he developed two equations. The initial equation is RQD equals 115 minus 3.3 multiplied by JV, where JV is the number of joints in a cubic meter of the rock mass. The alternative equation, published more recently, is RQD is 110 minus 2.5 times JV. This table shows the joint set number of the Q system. And you can see that there are values there related to the descriptions of the rock mass. So in our case, the rock mass that we are looking at, that blocky rock mass with 3 joint sets, the joint set number is 9. So Jn in this case equals 9. There are 2 notes associated with this table. The first one is for intersections, it says use Jn equals 3Jn. So that's effectively introducing far more joints. So it's taking into account the fact that at intersections you have bigger spans, and that at intersections usually you have subjected the rock mass to blasting on more than one occasion. So it's caused some deterioration. So it takes that into account by taking Jn equal to 3Jn. The second case is for portals, where, for example, a tunnel entering a rock face, or in an underground cavern where you have a tunnel intersecting the cavern. At that location, you have no confinement of the rock mass in the axial direction of the tunnel. So there's going to be less strength, you might say, in that rock mass. And to take that into account, Jn is taken as equal to 2Jn. Here we have the table for the joint roughness number, and it takes into account the large-scale roughness and the small-scale roughness. So you'll see on the larger scale, you have discontinuous, you have undulating, and you have planar as descriptions. And on the small scale, you have rough, you have smooth, you have slick and sided, and you have also cases where you might have gouge in the joints thick enough to prevent rock wall contact. And there's corresponding numbers to those descriptions. This table shows the joint alteration number. There are 3 columns, one for each so-called joint separation. In our hard rock conditions in South African mining, we tend to have fairly tight rock masses, so your separation generally is going to be in that first column, in other words, less than 1 millimeter. So we will tend to focus on those areas. The description of the gouge associated, or the condition of the joints associated with the joint alteration number are, the first one, tightly healed. That means that if you drilled through that joint, the core would actually be intact. We generally don't have that situation. Second description is unaltered joint walls, surface staining only. Third description, slightly altered, non-softening, non-cohesive rock mineral or crushed rock filling, and so on. And there you can see the corresponding numbers that correspond with those descriptions. So that's the joint alteration number. Joint water reduction factor. This is the table. And you can see, again, descriptions of groundwater conditions and the corresponding joint water reduction factor that goes into the calculation of the Q. Quite often in our rock masses we have dry conditions, and the JW value there is going to be 1. But clearly you would choose whatever is applicable to the rock mass under consideration. Here we have a table which deals with the stress reduction factor for competent rock and rock stress problems. There's also an equivalent table for much weaker situations, but because our rock mass conditions are generally hard, I think I'm going to ignore that in my lecture today. You can see the description: low stress near surface, and then the next column is the ratio between UCS and sigma 1 being the principal stress at the location at which you want the classification to be carried out. So, for example, if you have a rock mass in quartzite, for example, quartzite being a pretty strong rock with a strength of 200 megapascals typically, and that's at a depth of 1,000 meters, where the stress could well be something like 25 megapascals or a little bit higher. You can see that UCS over sigma 1 would be 200 divided by 25, which is going to give you a value of 8. And that will fit then into that third row down: high stress, very tight structure, usually favorable to stability, maybe unfavorable for wall stability. And the corresponding SRF value there would be between 0.5 and 2, depending on your engineering judgment of the stability conditions. So you can see that there are other descriptions here, and the descriptions in the lower two values are updates that Barton made after the original development, and it actually gives descriptions related to strain bursting and rock bursting, which is of interest to us in South Africa. Now it's time to apply these tables to our particular example of the rock mass. And here we have our blocky rock mass. And you can see 3 joint sets. You can see that the edges of those joints are very clearly defined, the edges of the blocks. You can also see that the surfaces of the blocks are pretty straight, so the joints are planar. And we can estimate from there also the joint spacings associated with those blocks based on the assumption of the 2-meter high poles. So if you have a good look at that rock mass to get a picture in your mind of that, and then I'll go through the calculation of a typical value of the rock quality designation RQD. So you will see we have 3 joint sets. Based on the fence posts, we can estimate that one of the joint sets has a spacing of about 1 meter. A second joint set has a spacing of about 0.5 meter. And the third joint set has a spacing of about 0.25 of a meter. We can use those to calculate the number of joints per cubic meter, which is the JV number, and that's given by 1 over those joint spacings. So it's 1 over 1 plus 1 over 0.5 plus 1 over 0.25, which equals 7. We substitute that into Palmstrom's equations, and we can get an RQD of 93% or 92.5%, depending on which equation is used. Barton recommends in the Q system to go to the closest 5%. So we will assume a value of 95% for the RQD. Here's the table for the joint set number. And as you've seen, we have 3 joint sets, so the joint set number is 9. So that is what we will use in calculating Q. The joint roughness number can be determined from this table, and the description that we would have that would be applicable to the joints in that rock mass that we're considering would be rough planar joints, and the corresponding JR number would be 1.5. So that will go into the Q calculation. The next description is the joint alteration number. Those joints were quite clearly not significantly weathered at all. They were not healed. So it's the second description that would be applicable there. It's a tight rock mass. So we would have unaltered joint walls, surface staining only, and the joint separation would definitely be less than 1 millimeter. So the JA number is going to be 1. The joint water reduction factor corresponds with what we observe as the water conditions in that rock mass. If there had been a lot of water in that rock mass, there probably would have been some evidence of weathering. The very sharp edges to the blocks indicate no weathering, and that's an indication that also there wouldn't have been much water around. So the joint water reduction factor there is going to be the first row, dry excavation, and the corresponding number is 1 again. The UCS of the rock, again from the exposure one can see that it's good quality rock. So let's assume that the strength is 200 megapascals. And if we consider a tunnel at a depth of 200 meters, say, the vertical stress there might be about 6 megapascals. So the UCS over sigma 1 ratio is 33 in this case. So if you look at the table, the row corresponding with that one is the second row, where UCS over sigma 1 is between 200 and 10, and the corresponding SRF, stress reduction factor value, for that is equal to 1. We come to the calculation of the Q value, and this is the RQD divided by Jn multiplied by JR divided by JA multiplied by JW divided by SRF. So you can see that from our numbers there we have 95 divided by 9 multiplied by 1.5 divided by 1 multiplied by 1 over 1. And that gives a Q value of 15.8. Now we can determine equivalent rock mass rating, Benioffsky's rock mass rating. If you remember earlier, I said it's very useful from a comparative point of view. And Benioffsky established a correlation equation between his RMR value and Barton's Q. And that is 9 multiplied by the natural log of Q plus 44. So the equivalent RMR to the Q value of 15.8 works out to be 69. Or Barton has also come up with a correlation equation, which is 15 log Q plus 50, and that gives an equivalent RMR value of 68. To put the correlation into context, this graph shows the relationship developed between rock mass rating and Q, and this is from data collected from the field. And you can see there that there's quite a lot of scatter between the two. So the use of a single equation could be somewhat misleading, but it is a guideline. And it's important that these correlations are made, because When rock mass classification is done, more than one system must be used. So you mustn't use only the Q system, or only the RMR system, or only the GSI system. You must use 2 or 3 systems and compare them, because they take into account different parameters, they treat things differently, and you might get significantly different answers for particular reasons. Let's move on now to Hook's GSI system. And Hook's GSI system is a graphical or descriptive system. You can see in this slide the descriptions are on the left-hand side, and they deal with structure. Under structure on the left-hand side, you can see intact or massive in the first row. Second row is blocky, and in each of these, Hook has given a good description. So for blocky, well interlocked, undisturbed rock mass consisting of cubical blocks formed by 3 intersecting discontinuity sets. The next one down is very blocky, and then blocky disturbed / seamy, disintegrated, and finally laminated or sheared. So the rock mass structure is indicating decreasing quality as you go downwards. If you look on the horizontal axis there, you'll see decreasing surface quality, and that's the surface quality of the joints. And you'll see the descriptions there, very good, and a description under that, very rough, fresh, unweathered surfaces. And the next description is good, and there's a corresponding detailed description under that, and so on, right down to very poor joint surface quality. Just up on the top left-hand corner, there's a general description, geological strength index for jointed rocks. From the lithology, structure, and surface condition of the discontinuities, estimate the value of the GSI. Do not try to be too precise. Quoting a range from 33 to 37 is more realistic than stating a particular value of 35. So you can see the diagonal lines on the lower right-hand side. Those give you the GSI values. The GSI is the geological strength index values. Here is our rock mass again, just to remind you what it looks like. Here you see the GSI chart, and I've highlighted on there what I think is the correct description for the rock mass that we're dealing with. You can see we have a very blocky, well interlocked, undisturbed rock mass consisting of cubical blocks formed by 3 intersecting discontinuity sets. And the number that I think corresponds with that, I've highlighted there, is a GSI value between 65 and 70. Hook recommends that a range of GSI be quoted, so GSI of 65 to 70 for this rock mass is applicable. Now, GSI also correlates with Beniowski's rock mass rating. And the correlation is GSI is RMR minus 5, or RMR equals GSI plus 5. So in our case, the corresponding RMR with our GSI is going to be GSI, the value that we got, plus 5, which equals 70 to 75. And that we must compare with the RMR from Q of 69. Note, an important note associated with the GSI, that it does not account for groundwater or stress. So if we do a GSI rating at a depth of 100 meters, we're going to get a certain value for the GSI. If we do it at a depth of 500 meters in the same rock mass, we'll get the same rating. Whereas, if you remember, the Q depends on the stress, so we get a different rating for the Q. This shows a simplification of the GSI chart, and it's something which you can use to get the rock mass rating value directly without thinking about the geological strength index. So it's a simplification which will make rock mass classification easier for you. Now we need to move on to Laubsche's mining rock mass rating system. As I said to you, Laubsche was working on the Zimbabwe asbestos mines at the time, and he took Beniowski's RMR, which he found unsatisfactory, and subsequently developed his own mining rock mass rating based on Beniowski's method. Laubsche's method is widely used in mining, particularly in block caving, which is where he developed it, and it's used quite widely in slope stability as well. I shall deal with the method originally developed. There have been some extensions to the method, and you should be aware of that. And if you're going to be a serious rock mass classification user, you should actually look into that. There are 4 input parameters. These are RQD, the rock quality designation, and Laubsche allocates a value of points rating of 15 to that. The second is the UCS of the rock, uniaxial compressive strength. Laubsche allocates a maximum value of 20 to that. And then he deals with joint spacing and the joint condition, including groundwater. So he's combined those 2 parameters into one, the condition and the groundwater. And the maximum rating for the joint spacing is 25, and for the joint condition and groundwater is 40. To determine the value of those, you have to look at the next slide, and there you can determine the adjustments to the spacing value of 0.5. So for our jointed rock mass, we determined spacings of 1 meter, 0.5 and 0.25. So our maximum spacing is 1 meter. So if you look at the graph here, you can see on the horizontal axis, if you go along to 1, and then you follow that line up until it intersects the first set of lines, the big dashed lines, you can see that the rating there is about 0.75. If you then look at 0.5 on the horizontal scale, and you take that up to the middle line, the intermediate spacing, the value is about 0.7. And if you then judge where 0.25 meters is, and take that up to the top dashed line, you're going to get a value of about 0.67, something like that. So those are the ratings that you would apply. The joint condition and groundwater parameter, the adjustments are determined from this table. You need to look at parameters A, B, C, and D, and then the descriptions and the corresponding ratings. The joint expression is the large-scale irregularities. In our case, we have straight joints and we have dry conditions. So you can see there in that third column, you have 70 and 79. That is the adjustment percentage. So if we look at an average there, we would have, say, 75% for that. In the B description, that's the small-scale irregularities or roughness, You can see the different descriptions there: very rough, striated or rough, smooth or polished. Our description was rough, planar, if you remember. So we're looking at between 85 and 99%, so we could assume a 90% reduction there. The third one is joint wall alteration. The descriptions are stronger than wall rock, no alteration, weaker than wall rock. We have no alteration in ours, so the adjustment is 100%. And then the last one is joint filling. In our case, we have no fill, surface staining only, so again, our adjustment is 100%. So we would multiply that peak rating of 40 points by these adjustments cumulatively. So our joint condition and groundwater rating will be, as you see on the slide there, 40 multiplied by 0.75, multiplied by 0.9, multiplied by 1, multiplied by 1, which equals 27. So the mining rock mass rating then is the sum of these parameters, which is a rating of 14 for the RQD, 20 for the UCS, 9 for the joint spacing, and 27 for the joint condition and groundwater. That totals up to 70, and again, we have very good agreement between the equivalent Q and the GSI. The mining rock mass rating is the same number, effectively, as Beniowski's rock mass rating. Laubscher's mining rock mass rating refers to the quality of the rock mass in situ before the effects of excavation are taken into account. These effects are taken into account by adjustments to the mining rock mass rating, resulting in the adjusted MRMR. There are 4 adjustments. First one is for joint orientations to take into account the ease of block fallout when an excavation has been made. Second adjustment is for the rate of weathering when the rock is exposed by excavation. Third one is for the method of excavation, for example, boring or blasting. And the last one is for the confining stress. Here we see the explanation for the joint orientation adjustments. In the first picture, you see 2 out of 6 faces away from the vertical. The second one is 4 out of 6, and the third one is 6 out of 6. Here are the joint orientation adjustments, so you can see that for our example, our rock mass, we have 2 joint faces that are away from the vertical. Those are the 2 horizontal faces, the top and the bottom of the blocks. You can see I've highlighted it there in the slide, and the adjustment then is 90%. The weathering adjustment, there's a description of how rapidly it's going to weather. This is the weathering adjustment, and you can see descriptions there of the time and the degree of weathering, and it's a judgment thing, and it would be based on observation and experience. And in our case, I've just said that it could be slightly weathered after a period of 4+ years, and that's a 95% adjustment. The excavation method considers boring, smooth wall blasting, good conventional blasting, and poor conventional blasting. And you can see, if we assume for our case good conventional blasting, Laubscher's adjustment there is 94%. This just gives an indication of further adjustment for the stress, the confinement, and this is based on engineering judgment. The minimum adjustment is 60%, and the maximum is 120%. And it just gives you an indication there in the pictures of what you need to take into account For example, on the left-hand side, a horizontal confinement would improve stability. On the right-hand side, a significant confinement might actually pop out those blocks because of the different orientations. So we can calculate an adjusted mining rock mass rating, and it will be 70 multiplied by 0.9 times 0.96 times 0.94 times 1.1 if we assume that we have an enhanced confinement. And that's going to give you an adjusted mining rock mass rating of 62.5. There are many other rock mass classification methods as well, which we're not going to use. The coal mine roof rating system, that has been used or tried out in South Africa and found not to be satisfactory for our conditions here. There's a Matthews-Potvin method, and that is particularly applicable in Canada and Australia for open stoping mining operations. Palmstrom developed a rock mass index, and there's a rock wall condition factor, which is not really a rock mass classification method, but is useful in our high stress conditions. I'm going to move on now to the uses of rock mass classification systems. The main uses are the evaluation of the stability of underground excavations, the evaluation of caveability, the evaluation of the stability of rock slopes, the evaluation of rock strength and deformation parameters for rock masses, and the evaluation of borability, and so on. It can also be used to determine the support requirements for rock masses. Evaluation of stability of underground excavations in rock masses. For example, if we consider a 10-meter span tunnel at a depth of 200 meters. This shows a chart developed by Beniowski, which correlates the span of an excavation with the rock mass rating. And on the chart, you can determine the stand-up time of that excavation. And I've highlighted what we have got in our case, corresponding with 69 for the rock mass rating and a span of 10 meters. And you can see that the stand-up time there is between 6 months and 1 year, probably about 10 months. That means after you've excavated, after you've taken a blast, it's going to stand there for quite a long time before it becomes unstable. This is the output more recently of the Q system. It's the Q system stability chart. I'm not going to deal with it here because I have a version which comes later in this lecture. Slide 87 is a very much simplified form of the previous chart. It's something that I've developed from the previous chart, and I've made it slightly less conservative than Barton did in that chart. And I've also put on here the highlighted point for our particular rock mass. This is a relationship between Q on the horizontal axis. I've got RMR at the top and the unsupported span. So again, we have 10 meters and we have our value of 69 there for the rock mass rating. And you can see those lines represent factors of safety. And the factor of safety corresponding for our tunnel is a little bit greater than 1. So that says it's marginally stable, and that corresponds with the stand-up time. There's going to be a certain stand-up time, and then ultimately you're going to have some failure. So the implication is that you need to be able to install support to provide the required stability of the tunnel. Rock mass classification can also be used to assess the stability of raised bores, and what has been developed is a modified Q system, and it takes into account face and wall orientation adjustments, a weathering adjustment, and a wall adjustment to the Q system. This is the output which gives you a correlation between a Q value for the raised bore quality. In other words, that's the modified Q taking into account those adjustments, and the raised diameter. And it gives an indication of the probability of failure or the reliability of a raise. Rock mass classification can also be used for the prediction of caveability and caving angles. The prediction of the required undercut dimensions in block cave mining for propagation of caving is an extremely important thing, and that's actually got to be done for the development of any block caving layout. This shows empirical data that Laubscher collected correlating his adjusted mining rock mass rating on the vertical axis with the hydraulic radius of an excavation. The hydraulic radius being the area, the plan area of an excavation divided by its perimeter. And he's collected data for various mines from across the world. There's data there for Zimbabwean mines, South African mines, Canadian mines, and Chilean mines. And the two lines represent, the right-hand line one is on the right-hand side of that. Anything that plots there, caving will propagate. Between the two lines is the intermediate stage, and the left-hand line, or the upper line, is the initiation of caving. So when you have something above that upper line, it's going to be stable. So you can use that to estimate the required caving undercut area and the initiation of caving as well. I mentioned the Matthews-Potvin method. Potvin produced a stability graph method. It's a modified Q system. Instead of two of the Q parameters, it introduces two others, and those are the adjustments for stress to strength and the ease of block fallout and gravity adjustment. Slide 93 gives you a graph which corresponds with Laubscher's graph. It shows the modified stability number N, which comes from the stability graph calculation. And on the horizontal axis, again, you have the hydraulic radius. And you have two lines there. The lower line is caving. Below the caving on the right-hand side, you have failure. In between is intermediate, and above is stable. And obviously for open stoping mining operations, you want to design stable stopes. There are major consequences if one gets the prediction wrong. There are huge financial consequences, and there can be safety consequences as well, both in open stope mining and in block cave mining. Here we see the chart again for evaluating the factor of safety, and that can be used to give a prediction of the initiation of caving as well. We've found from use of this chart that a factor of safety of around about 0.6 to 0.7 gives an indication of that initiation of caving. Laubscher's method can also be used for the prediction of caving angles and the extent of the cave crater. This is a cave crater, what happens to the surface after block cave mining, and this is at Shabani up in Zimbabwe. This is in the Chile in the Andes. And you can see there the caving that has taken place as a result of mining at El Teniente mine. Laubscher correlated the caving angles that he'd observed on various mines around the world with his adjusted mining rock mass rating. And this table shows that correlation. There are two conditions: lateral restraint to the side walls of the cave crater, and if there's no lateral restraint, that's another condition. And he considers two depths, 4 cases. So for example, if there's no lateral restraint at a depth of 100 meters for an adjusted mining rock mass rating of 50, the angle predicted is 60 degrees. At a depth of 500 meters, that prediction would be 50 degrees. If there is lateral restraint, the prediction at 100 meters depth would be 70 degrees, and at a 500 meters depth, it would be 60 degrees. Rock mass classification can also be used for the evaluation of the stability of rock slopes. Romana in Spain developed an approach which is based on Beniowski's RMR and adjustments. I won't describe that here at all. The second one is Haynes and Terbrugge, who developed a chart based on Laubscher's adjusted mining rock mass rating, because Laubscher, in his evaluation of case studies, could also determine overall slope angles for cave craters, and he correlated that with his adjusted mining rock mass rating. This is Laubscher's correlation between the adjusted mining rock mass rating and overall slope angle. And this is the chart that Haynes and Terbrugge developed as a result of Laubscher's original correlation. It shows the adjusted mining rock mass rating on the horizontal axis and the slope height on the vertical axis there. And if we look at an example of a triple bench stack, for example, with 60 meters high, you can see there highlighted the rating for that. And that corresponds with a slope angle which would be recommended of about 59 degrees for a factor of safety of 1.5, or 69 degrees if you're happy with a slope factor of safety of 1.2. What is the effect of blasting on slope stability? The chart can be used to assess that, because Laubscher's classification method has the blasting adjustment. His adjustment for blasting, which we used, was 94%. But if we look at poor blasting adjustment, we can then get an adjusted mining rock mass rating of 62.5 multiplied by 0.8 divided by 0.94, and that gives 53. So we've reduced the adjusted mining rock mass rating from 62.5 down to 53. And if we plot that on the chart, you can see the result of that. It plots round about 54 degrees for a bench stack. That is 5 degrees different from what we had before. So the slope angle for good conventional blasting was 60 degrees. Slope angle for poor blasting was 55 degrees. What is the value in money terms associated with a change in slope angle of an open pit? Does any of you know? Well, my estimate for Palabora mine was about R500 million per degree. So you can see that by saving a little bit of money by poor blasting, you're actually destroying a lot of value. Rock mass classification can also be used as the basis for determining rock mass strength and deformation parameters. The Hoek-Brown parameters for the rock mass can be determined from equations which include the GSI, and they include the D value, which is a disturbance factor, which you'll see in the next slide. The use of these parameters are obviously applicable in the Hoek-Brown criterion for rock mass strength. This is just a graphical and descriptive terminology for the different D factors there, and you'll be able to judge from good blasting, poor blasting, and so on, which D value to use in those previous equations. Rock mass strength and design rock mass strength can be calculated by a method that Laubscher developed, and his calculation is really an adjustment of the intact or uniaxial compressive strength of the intact rock material. The rock mass strength is determined by multiplying the UCS value by a ratio. So if you take the mining rock mass rating and you subtract the rating in the classification system that you used from that, and then divide it by 100, that is how you get the rock mass strength. The design rock mass strength is then the rock mass strength adjusted for the effects of the disturbance when you create the excavation. And you take into account the effects of weathering, joint orientation, and method of excavation. You don't take into account the effect of stress or confinement in this case. And that's quite a useful way of determining a rock mass strength, which you can compare then with the stress that you would have in the mining environment. Barton also developed an equation for rock mass strength, and you can see that on the slide. Unfortunately, all of these methods for determining rock mass strength give different answers for the rock mass strength. So you have to use engineering judgment to decide which number you're going to use in your rock engineering application. Regarding deformation, several equations have been developed correlating the rock mass modulus of elasticity as a function of the rock mass rating, or Q. This shows a plot of the relationships between rock mass moduli which have been measured in the field and their corresponding rock mass classification values. And you can see that there's quite a lot of scatter, and thus a single equation is of doubtful validity in many cases. Rather than a direct prediction method, rock mass modulus is much better estimated from rock mass classification data using a reduction factor relative to the intact rock modulus. The modulus prediction formula developed by Hoek and Diedrichs appears to work well. And there you can see the equation there, which takes into account both GSI and the disturbance factor as well. And that appears to work pretty well. EI in that case is the intact rock material modulus. I'd like to move on now to another use of rock mass classification, and that's for the estimation of rock support requirements. Barton, in his original publication in 1974, had a chart which defined different categories of support associated with rock mass classification numbers, the Q value. And from those tables, one could determine the support recommendations. Subsequent to that, a single chart has been developed. This relates the span, or the height of an excavation, divided by a form of factor of safety against the rock mass quality. And it's quite a complicated chart, but you can see that from that you can estimate what type of support is necessary, and that is rock bolts and shotcrete or steel fiber reinforced shotcrete. This shows an earlier version of the Q support design chart, and you can see the white area in the white sort of block in the middle. That is where the system works best, and that corresponds with hard rock in general. What I did was to take Barton's original chart and simplify it so that it's easily applicable. And you can see here the relationship is between span and Q, and on the top you've got RMR. So in the different bands there, those reflect square meters per bolt. Not bolts per square meter, but square meters per bolt. And we could use that for our 10-meter tunnel as an example. With the rating that we had, we've got RMR of 69, a 10-meter tunnel, and that corresponds just marginally with no support required, or 5 square meters per bolt, something like that. But the implication is that you need to put some support in there. This gives a correlation for shotcrete and fiber or mesh reinforced shotcrete. In the clear areas, you can see the numbers there refer to the thickness of shotcrete, and the blue shaded area is where fiber or mesh reinforcement is required. And you can clearly see here that for that 10-meter tunnel, no shotcrete support would be required. One of the other things that is necessary in support design is the design of the bolt length, and Barton gave various equations for that, and those equations can be used to estimate the lengths of rock bolts and cables, and they correlate with obviously the rock mass quality. Laubscher also did that, and there he's got little equations which can be used for his conditions as well. You will find that you will get different lengths of support if you use Laubscher's or Barton's. Laubscher, working in a block cave mining environment, believed that when you put support in, you really needed support. So his bolt lengths will tend to be longer than Barton's. Here we have an exposure of rock, and you can see in the lower portion there, you can actually see joints, you can see the rock surfaces exposed and so on. Just have a good look at that and have a good picture in your mind as to what that rock mass looks like, and then we will do a GSI classification of that. There's no doubt that that rock mass would be described as very blocky. And there's sharp edges to the blocks, but there's a lot of discoloration as well. So the value for that would probably be in the range of 50 to 60 for the RMR. Now, if we consider our real problem, we're looking at an excavation with a span of 65 meters. So we have our rock RMR value between 50 and 60, say 55 on average. And the span is 65 meters. So the recommendation for the bolt spacing is 6 square meters per bolt. If we look at the requirement for shotcrete, you can see corresponding with the 55 value and a 65 meter span, the recommendation is 100 millimeters of shotcrete. So those are the support recommendations. The actual recommendations for that is the problem. It's an ice hockey cavern which was created in Norway for the Winter Olympics back in the 1990s, I think. These are the actual numbers corresponding with that ice hockey cavern. The span, 65 meters. The actual average RMR determined was 58. Our estimate was 50 to 60 or 55 on average. So it took us a minute to determine that. The support actually installed was rock bolts and cables on a 2.5 meter grid. We estimated 6 square meters per bolt, and the square root of 6 square meters is about 2.5 meters. And there was 100 millimeters of fiber reinforced shotcrete. We found 100 millimeters of shotcrete, but I did say that those charts I had deliberately made less conservative so that they would be more applicable to mining conditions. So you can see that in a few minutes we've actually come up with a design for that cavern which was implemented based on rock mass classification. So it works. That's not an indication that you can do your designs only by that. For an excavation as important as this, there was a lot of other engineering put into the design of the support. But rock mass classification is very, very useful as an estimation of support. There are many other applications and correlations that have been developed with rock mass classification. One of these applications is the prediction of tunnel boring machine performance, and both Barton and Beniowski have developed systems for that, and those are applied now with varying degrees of success. There have been strong criticisms of the Q-based system, and I've, in my application, feel that Beniowski's system tends to be better. But Barton is certainly confident in his own system. Finally, I've given you a very brief introduction to rock mass classification. You will need to study the rock mass classification literature to gain the detail and the detailed understanding associated with any method that you might use. I've given you my approach. With practice, you'll develop your own approach. There's no perfect answer, and I've seen data published that shows that many experts doing the same rock mass classifications of the same sites actually get different numbers. So there will be some difference in the data that you get out. Variability needs to be taken into account, and I emphasize that. When used properly, rock mass classification can be an extremely powerful tool, and it's made a huge difference in rock mechanics and rock engineering, in mining and in civil engineering. Thanks for listening.